Okay, here we are. This is the last video lecture before the review, so we'll try to tie things together. It's the Physics 105B video lecture 43. So we've been doing a little bit of fluid mechanics, so let's review a bit of that, and I'll try to tie things together. Love to do a whole lot more, but we're going to save that for our Physics 190 1-unit course, in which we'll be able to get a little more of this great material here. Okay, so for fluid mechanics, I'll write down our equations once again and discuss them a bit. And then the application that we did, the rotating bucket, I can say a few more words about that, and then we'll do one more important topic. So what we have is the Euler equation, which is dV dt v dot gradient operator acting on V equals minus 1 over density gradient of the pressure, and then we have the continuity equation, and that is d rho dt plus divergence of rho v equals 0. And then we have entropy, and when I just write S equals constant, I'm just using the fact that we have no dissipation, no energy dissipation in an ideal system like this. Okay. Good. So the first application was the rotating bucket. And what we had was some volume of fluid, and here's our coordinate system, x, y, z, and we're rotating, and we've got omega along the z-axis, so omega is equal to 0, 0, omega. It's a constant rotation. And the velocity that goes with that, we just inherit from a rotating solid. So it's omega cross r. And I'm going to let r just equal x, y, 0. So we're really just talking about the two components, and otherwise it's rotating uniformly throughout the vertical axis. Okay, so that's what we use to show that we have this paraboloid surface of rotation, which is interesting in itself. Next, let's consider V equals same omega cross r to the nth power times the vector r. And this is why I'm just using the x and y. Okay, I want this root x squared plus y squared. So we've got that uniform symmetry up and down. We don't want the z component in this thing right here. Okay. So what do we have here? N equals 0, then that is this rigidly rotating bucket. And the other one that's really interesting is N equals minus 2. Okay. And I'm going to save this for next semester, just discuss it briefly. What happens here is if you calculate the curl. So the curl of V, you'll find a non-zero curl for all values of n except n equals minus 2. And that's a property that you also have in magnetic fields. Okay, that n equals minus 2 means you have a velocity that's proportional to 1 over r in its magnitude. Okay, very interesting field. In general, the curl of a vector field is really important, and in fluids, it's of fundamental importance. So you can calculate the curl of this here, n equals 0 case, and you trivially get a positive constant, and you can test your result with Stokes' law, Stokes' integral theorem. You do it for n equals minus 2, you get a bit of a surprise. So I'll just write here, check. We'll do this next semester, okay? But it's an extension of what we were just doing right now. Check n equals 0, n equals minus 2, right? And think about that. Good, so that's the one application and a little discussion of where it's going. The second application, what we're going to do is linearize these equations. Now, we had done linearization when we were talking about stability analyses earlier in the semester. And so linearization is just the thing to do here and see what happens. So next to linearization of the fluid equations. So we're going to linearize, and what we're looking at is small quantities, okay? We have the fluid equations in this case. For the case rho is not constant. Okay, so we're talking about a compressible fluid now, not an incompressible fluid. This example up here, we were using divergence of V equals 0. In this case, we're now taking rho not equal to constant, i.e. divergence of the velocity is not equal to 0. But if we're doing a linearization, V, of course, is going to be a small quantity. Okay, so we have the following. We have V is small so that the nonlinear term, which is this one, can be dropped. Okay, that's what it means to linearize, so that V dot grad V can be neglected. So that's the first thing. Then, rho is not constant, but it's the first approximation to rho being constant. So let rho equals rho 0 plus rho prime, P equal P0 plus P prime, and these are the constant, you could say equilibrium values, and these are the small quantities, okay? So rho 0, P0 are constant, and rho prime, P prime are small. So that's what we're going to assume, and then we'll go into the equations of motion. So let's go ahead and first of all deal with the continuity equation. So now we have d dt rho 0 plus rho prime plus divergence of rho 0 plus rho prime times v. Remember, v is small, so we don't have a v0 plus v prime. V is already small. Equals 0. And we expand that out. Of course, the row 0 is constant, so that's gone. So we have d rho prime dt plus divergence of row 0, that's gone. Oh no, like this, plus row 0 divergence of v. Right? Row 0 you pull out divergence of v. And then we'll have divergence of rho prime times v plus divergence of rho prime v equals 0. Now, v is small, rho prime is small, therefore this is second order small. And we can toss it, get rid of that. So now we have, and we'll put a box around it. So one of our linearized equations has already been obtained. D rho prime dt plus rho naught divergence of v is equal to 0. So we got that one. Send it up. Okay. Let's go ahead and leave these up there just to look at them, right? So we have this, and we have to linearize this equation, which I think is quickly done. But again, this was already, keep going with the numbers, this was already declared small. So we have dv dt plus nothing equals minus 1 over rho naught plus rho prime gradient p naught plus p prime. And that's it. Okay, so this is also easy to deal with. The gradient p naught, of course, is 0, so we just have a gradient p prime. If we were to expand that out, the next expansion term would be a second order small. Let me go ahead and do this. This would be minus 1 over, I'll do the calculation. So I have 1 over rho naught, 1 plus rho prime over rho naught. Okay. And the expansion of this is 1 over rho naught, 1 minus rho prime over rho naught. But that's if you expand this thing out because it's in the denominator. And I think I can just work talking about it here. So we're going to keep the 1 over rho naught. Right? The gradient's going to be p prime. And if we were to include this rho prime over rho naught, it would be a second order term again. Okay. So because of that, this simplifies to, I'll go ahead and write this right here. Negative 1 over rho naught gradient p prime. Okay, so now we have that linearized. These two equations linearized. Right, so let's make sure I get the next step. 1 over rho naught minus rho prime over rho naught squared. Okay. Point is if you include this term, when you expand this out, you're going to have a small times a small, and that's going to be second order small. So there you have it. There's one more thing we need here, and that has to do with this equation here, we're going to want to express the pressure in terms of the density and vice versa. And we can do that. So if P is taken to be a function of the density and vice versa, P of rho, we can imagine expanding it out, and then P would be P of rho naught plus rho prime, which would be P of rho naught plus dP d rho evaluated at rho naught times rho prime. So you'd have this right here, okay, so P. On the other hand, P go ahead right here. P equals P naught plus P prime. That's what we said before. Do I have it up here? Yeah. P naught plus P prime. Constant plus small perturbation. So because of that, we can identify P prime with dP d rho, value of rho naught times rho prime. So let's take that. P prime equals dP d rho prime. Remember, those aren't derivatives, those are just small quantities. And here we have to make use of this entropy constant. So this is the derivative of pressure with respect to density evaluated at S equals constant. Here we could say S naught. And you know, obviously at rho it equals constant as well. So that's important. So we've made use of everything that was on our list of fluid equations, and now we just have to put these three together to see what happens. Okay, so hold on to this, erase everything here. We'll go ahead and start with this equation and take the time derivative of it. Yes, so now take, still numbering things, why not? Now differentiate equation star with respect to time, and we will have d squared dt squared of our rho prime equals minus rho naught divergence of dv dt. Okay. We'll just exchange the order of differentiation. Then we've got the minus rho naught and the divergence of dv dt, but the divergence of dv dt dv dt is minus 1 over rho naught gradient p prime. So we have minus 1 over rho naught gradient of p prime. And now we just have to be careful. We've got the minus and the minus, get rid of those. Rho naught over rho naught, they're already gone because they're constants. So we end up with the divergence of the gradient of p prime. So what do we have for p prime? P prime is dp d rho prime. So we have dp d rho, I'll just write the constant s like that, times rho prime. Now this derivative of one function with respect to the other, a constant s, is itself a constant, right? It's a derivative in an expansion, so that's a constant. So we can pull that out. Let's go up here. So we now have d squared rho prime dt squared equals, pull this out, d e d rho constant s, and then we have, having pulled that out, we have div grad rho prime. And div grad, of course, is del squared rho prime. And this is recognizably the wave equation. So it's the wave equation for the density, right? A little perturbation of the density, you could say. Wave equation with wave speed c. I'm just going to call it c because we're already taking care of velocity, and v is present too much here. So wave speed is c, has nothing to do with the speed of light. It's just the wave speed c equals the root of dp d rho constant s. So good, now let's go ahead and write what we have here. We have d squared rho prime dt squared, make that a little nicer, dt squared equals c squared del squared rho prime. There's our wave equation. And you'll notice that because p prime and rho prime are just proportional to each other with a constant in front here, speed of sound, back to this, yeah, right, speed of sound squared. I should point out. So now we have a wave equation for the density. We have the wave equation for the pressure, and those are sound waves. Okay, so this is the wave equation for sound in a compressible fluid. So let me go ahead and write that down. Wave equation for sound in a compressible fluid. And you also see the greater this derivative, the greater the speed of sound. The change in proportionality between pressure and density, essentially. So for example, in a solid you'll find, or in a liquid you'll find that the wave speed is much higher than in a gas, okay, because of that compressibility. And again, because of the proportionality here, we have the same thing for pressure, E prime. We also have a wave equation, same speed, density, and pressure, of course. What about the velocity? There's also a wave equation for the velocity. I'm going to save that for later as well. We can go in here with the same calculation we've done for the velocity. Right here, we could take a time derivative, d squared dt squared v, and go in here. When we do our grad div, however, in order to obtain a wave equation, we have to know that the curl equals 0. And we didn't prove that this semester. So, right? We'll prove that later. So we've got our wave equations. Let me also remind us, we had the one-dimensional wave equation for the chain of masses in the limit of in the continuous limit. We had that when we were doing Lagrangian mechanics and small oscillations. So this extends that. Okay, because now we're in a continuum, we have all three dimensions, not just a one-dimensional wave equation. So we were able to tie things together in that regard as well. So I'm just going to put here next show that, and we'll pick that up as well. We can complete all these things and a whole lot more. But the next step would be to show that d squared v dt squared is c squared del squared v, right, which is three equations, if curl of v is equal to 0. Well, curl of v is not always equal to 0, so that's something we have to come in there and separately determine that the curl of v is 0 under the conditions of wave propagation. Okay, so we can show that. And next, also, we can prove that the sound wave is a longitudinal wave. Prove that sound wave, which is what this is, sound in a compressible fluid, is longitudinal. Which is the kind of thing we're just told, but we don't necessarily prove, but we'll get it rigorously and formally out of the formalism. So that's one direction that fluid mechanics takes, the whole study of sound in a fluid. It's called acoustics, and there's a lot going on there as well, musical instruments and so forth. I think this is a good place to end. The next and final lecture will be a pure review in which I go over everything that's going to be on the exam. Okay. So until then, see you next time. Good.